The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show. Karen, what are we going to do in today's episode?
Why don't we take one of the build ideas from a top 5 build winner?
Oh yeah, every month we pick the top 5 build ideas from the community, talk about them, and then consider them for future builds. What do you have?
So I like this one submitted by Gorilla Grew, where he essentially wants us to make the ultimate retro gaming controller.
Like a universal controller that works on multiple systems?
Yeah.
Okay, he talks about using a DB9, which is like the plug on the Atari or the Genesis.
Okay.
It might be cool to do a wireless solution.
Oh yeah.
Yeah, we could use the inexpensive ESP8266 module and have like a transmitter, controller, and then a receiver on the game console, so it could be wireless and universal. We could shoot for like maybe 3 consoles, like Nintendo, Super Nintendo, Sega Genesis, Commodore, Atari. What do you think?
That sounds perfect.
Let's get started.
Amazing hacks.
Where are my dragons?
Inspired designs.
Oh, like I knocked some hot glue loose.
Regrettable acting.
I want to live in a world with Star Wars again!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Okay, so this retro controller, Karen, right? Here's my plan for
Gotta
it.
be ultimate.
There's this module you can get called the ESP8266.
Okay.
It's a really low-cost Wi-Fi module, and you can program them using LUA. They run a firmware called NodeMCU. So you write some script in Lua, NodeMCU executes it, and then the 2 modules can talk to each other. So I'm thinking we'll have a controller module, which will be the transmitter, and then a console module that will be the receiver. Yes.
Okay.
So here's my plan. We build a controller like this, and it has shift registers in it, and those shift registers will read the buttons. So we'll have 16 bits, because there's not going to be more than 16 buttons. And the module can shift the data out of the shift registers and into itself, which is pretty much exactly how a Nintendo controller works. So this basically just reads in 16 bits. It doesn't care what the buttons are for each console, it just gets the data. Then it transmits a 16-bit package, which would be 1 word, to the receiver unit here. The receiver takes that data and recreates it on its side with 2 more shift registers. But these would be output shift registers, which are 74HC595. So each one has 8 bits, again, the 16-bit word, and it's going to be 0 or 1. From that point, we then connect up the console plugs. So let's say you've got Nintendo, Super Nintendo, Genesis. So the way we connect these plugs to these shift registers depends on what the buttons actually do. So after we wire it all up, we'll actually use the multimeter and test these points to see what the values are. So we're like, oh, okay, that's A, that's B, that's up, etc. And then we wire up our controllers to match.
Okay.
Now, each controller is different. In the case of the Super Nintendo and the Nintendo, there's going to be input shift registers. So we'll actually take the output shift registers and connect them to the input shift registers. So when the Nintendo wants data, it pulls it out of those shift registers. For the Sega Genesis, I think what we'll do is we'll just take apart an old Sega Genesis and get the chip out of it and hook that chip, or the pads that would be on the chip, directly up to the output shift registers as well. So 1 bank of output shift registers, 3 different console inputs. And it'll be all wireless. So in this controller, we'll have the module, a battery, charge jack for the battery, and it'll be self-contained. And this receiver unit will be powered off of the console because the consoles all have 5 volts somewhere on their plug. I think we'll start by building the transmitter controller. Once we have that working, then we'll build the receiver and then test it on the consoles. Felix wired up this shift register test. It has 16 lights and 2 74HC595 output shift registers. That should work great for this project. Let's see. 567 MOSI latch clock. So let's see, here's latch and clock. So in the controller, we're pulling data off of the shift registers. In the server, we're putting data onto the shift registers. So these shift registers will be what connects to the actual game console, basically acting as digital I/O buttons. All right, let's plug it in and make sure nothing blows up. We're also getting power off of this.
Okay.
Okay, I saw something blink. So we haven't found the AND operator yet for Lua. Lua doesn't have any bitwise operators built in, at least not the version of Lua that we have, unfortunately. So right now it prints the received data. Let's also go to what we call shift out.
Yeah.
Let's also call that function as well. shift out.
Oh, we're gonna need to reconnect to the module as well.
Yeah, let's try connecting to it again. You ready?
Yeah.
Hit open.
Okay.
There it is.
Yay!
All right.
Right on.
All right, so before we send it a bunch of data and fill it up, let's resend this. Let's send one copy of shift out at the start to make sure that our code is working. All right, so shift out, outputs equals 0. For I equals 0 to 15, so 16 iterations. If outputs equals 1, then, wait, do we have to do brackets around the if then? I can't remember.
No, I don't think so.
I don't think we have to, yeah. Felix and I are both Lua noobs. Apparently we uploaded the file. Let's see if it's still there.
Success.
I'm gonna reset it.
What was the issue that it was having?
I don't know, try closing the port again. Open it, there you go.
It's live.
Okay, it should do something with the LEDs when it gets a signal from here. I don't know if it will, but we'll see. Well, it's getting a signal from here, but the LEDs aren't doing anything. That's a file. I think we need the scope.
Okay.
I'll go get the scope. If your breath smells, get scope. Brand mouthwash.
Well, I'm trying to figure out what the problem is with this inconsistency that we're having with the GPIO. Right now in the code, it says it makes the server, and then when it receives a connection, it'll shift out some bits, okay? So now we have the scope hooked up, and the blue line, of course, that's still the client, and the yellow is the server. And I'm going to stop this right here. You can see the inconsistency where the spikes on the blue here, there are not spikes on the yellow. When there's supposed to be a signal here and there's not. So I'm trying to figure out why that is happening. Over here in the code, we got the server up, and then when the server's on and oh, maybe, so I think I need to figure out what server on is doing. Well, I'm going to continue working on this. Hopefully I can find a solution, and if and when I do, I'll let you know.
Made some more progress. I stumbled around in the Lua documentation some more, and I found out how to use strings. So what I'm doing is I'm creating a string that has a left bracket, then 16 zeros or ones based off these buttons, and then an ending right bracket. And then I'm just doing one command, which is socket send string, and that's what is sent to the server now. And on the screen here, we can see a whole bunch of ones. I was looking into the AND bitwise libraries, and yeah, it's a lot of overhead to try to like turn variables into bits in Lua. So I was like, you know what? I'm just gonna use strings. I'll just send 16 zeros or 16 ones, and I can decipher that on the other end, which will probably also be a pain, but check this out. When I push these buttons, the numbers change. So when nothing's being pressed, it's a 1, and then when you push the button, it becomes a 0. I mean, we could use any characters we really like, it doesn't really matter, but I'm using these because these are what's correct. All right, so I have the proper data going to the server. Now all I have left to do is create something that takes apart the string on the server side on the shift register, and it's like, okay, is there a 0? I don't send a bit. Is there a 1? I send a bit, clock out 16 of those, and it should reproduce these buttons on these lights. And then we'll have communication, finally. I have this drawing here. There's multiple sketches now that create this object. We have the front half, which I've used acrylic to represent so we can see through it. I've started to draw in shoulder buttons here and here. The shoulder buttons will interface with the PCBs like this. So you can see the shoulder button touching it right there. One problem that we might have is there's really no place to put a shoulder button on the other side. So unfortunately, we might have to redo this PCB and make it bigger. I also need to think about how much space is in this case. So if this board is here, and the battery is here, and the charge circuit could go like right there, which means we pretty much just have this space here to put buttons and lights in. So again, what I might wanna do is rebuild this, have the PCB a little higher so we can have the shoulder button on it, and then have it come out this way so we can have start, select, sync, and power indicator. What I think I'll do next is print another iteration of the case that accounts for the shoulder buttons. So I'm just using up this old spool of blue plastic that I don't care about anyway. Believe I have this all done. So I made this again to make it a little larger, and everything's in one piece. So we have shoulder button, the client unit, and we can still get at the programming headers from the back, shift register, power switch, This is where the battery's gonna go and the charging circuit, and then of course we got a PCB over here. There's a few wires between this side and this side. We'll just snake those under the battery. Or what I could do is I could make a little bit of a chamber or groove in the 3D printed part. So yeah, I'm just gonna double check this and then I'll take it over to Felix and we'll program it to make sure that it was working correctly. I mean, Felix is using the first module that I built to do some speed tests. So that's why I built another copy of it, was so he was able to keep working. But yeah, it's a pretty nice compact unit.
The Warp 7 is a tiny development platform that's ideal for developing wearable technology and Internet of Things products. Use the Warp 7 to build wearables such as activity trackers, smart watches, or smart clothing. You can even use it to build innovative IoT products for smart home, city, or industrial applications. Purchase the Warp 7 development platform on element14.com today.
I'm mapping out the parts to make the video game console side of this. We have a 3.3 volt power regulator. Luckily, all the consoles have 5 volts at their plug. This is the server module that will plug into these 74595 output shift registers. These are input shift registers, the same kind that we have on the controller side. These will hook up to the Nintendo and the Super Nintendo. I'm still double checking the mapping. I'm hoping I can make it compatible. We'll see. Then I have some 74157 quad muxes, and this is what we'll need for the Sega Genesis controller. Should only need one of these, but we might be able to make it 6-button Genesis compatible as well if we use 2 of these. So I'm just gonna arrange everything like this on a bus, and then hopefully it'll all work. Yeah, so basically Super Nintendo, Nintendo, Atari, Sega Genesis, Master System. I printed the front of the case using stainless steel PLA from Proto Pasta. It's actually very sturdy and kind of heavy too. So we'll sand this up and it'll give us a nice cool look, and then maybe the back of it we can do in black carbon fiber and then laser cut some plates for the front. It'll look really cool. Max and I did some tests with the transmitter and the receiver. Obviously we don't have the second shift register over here, but we were able to map the first shift register, and here are all the mappings. Left shoulder, start, select, no connection, left, down, up, right. And then this will have the other buttons such as X, Y, Z, and what is it, right shoulder? So something I realized was we could pretty much make the Super Nintendo and Nintendo parts compatible. I've got this old data sheet I printed years ago. So yeah, this shows how the Super Nintendo uses 2 shift registers to send out all the data, whereas the Nintendo only needed 1 shift register. And they're actually pretty much compatible. See how the output here has all the Nintendo buttons? You can do up, down, left, right, A, B, select, start, and then it adds Y, X, left and right bumpers. What we can do basically is the plug that goes to the Super Nintendo and the plug that goes to Nintendo can be wired the same way. The only difference is the Super Nintendo is going to shift out an extra 8 bits to get the second register. So that should work out pretty well. All right, so we have a 3.3 volt regulator. This is a jumper, so we can choose whether or not we're using it. For testing purposes, we'll leave the jumper in place. We have the server module hooked up, added a reset button. I'll probably also add a LED to the latch line so we can see activity on this. And yeah, we have a power rail, a ground rail. And what we're gonna do next is attach all the support chips down the path. And again, we should be able to do it with just 2 chips for the Nintendo, Super Nintendo, and 2 chips for Atari, Commodore, Master System, Genesis. Originally, I thought about putting the plugs right onto this board, but then I realized, you know, depending on how your console is oriented, you might not be able to get it in. So what I did was I just grabbed some old crappy controllers from my basement and I cut the plugs off so we can use these. Actually, what I probably should do next is try to get this together. That way I can get all of the bits shifted out once I connect both halves of this, you know, the D-pad and the button pad. Yeah, I think I'll do that next actually. That way I have all the proper data going to the receiver. Okay, I got this together enough that we should be able to have communication between this shift register, and the client unit. So now Max and I can map the final few buttons, and then I can finish wiring up this. Let's make sure everything still turns on. All right, so I'm gonna need your help mapping this. Go ahead and turn it on. See if it gets a connection. Okay, it looks like it's connected. All right, I have no idea, so just push the new random buttons. Tell me what they are when you push each one.
B, C, X, Y.
Oh, there it was. Yep, try it again. Copy that. All right, test them all again. It's probably the one right next to Z though, if I had to guess.
Okay. Y.
Nope.
X.
Try C.
C.
Bingo. All right, let's find the next one.
All right. A.
Nope.
B.
Nope.
Shoulder.
That may be a no connection. Nope. All right, try them all again.
A. B, X, Y, shoulder,
Not getting anything off that one. Let's go backwards from this pin. All right, try them all again.
A, B, X,
There's X. Yeah, actually, there's multiple unused ones on the second chip. Okay, cycle through them again.
A, B, Y,
There's Y right there. Okay, it leaves A, B, and shoulder, right? Moving to the next pin, go ahead.
A,
That's it right there?
B,
Yep. So the only one we're missing is that right shoulder button. All right, ready? Go ahead, push it, let go, push it. There it is.
sweet.
All right, that's all the info we need. I've mapped all of the outputs on the receiver shift registers to match what's going on with the controller, so that part's good. What I'm doing is I'm going through and I'm wiring everything system by system. So in this case, I've wired the shift registers to the other shift registers to create the Nintendo output. The Super Nintendo output will actually be hooked up the same way as this. I mean, you could almost put this through an adapter and it would still work. It's the same pin out, except for it will use both shift registers. So here I've got the Nintendo buttons, which are up, down, left, right, select, start, B, A. And then here I will add left shoulder, right shoulder, X, and Y. Then I'll probably test this to make sure I'm on the right track with the Nintendo. And then I'll move on to the Sega Genesis right here. So I think I'll finish wiring up the Nintendo part of it, and then I will go back to work on this because I can pretty much completely finish this now. I don't need to do any more soldering, it's all done. So I might as well make this look nice and then finish up the receiver. Let's go over the parts. We have the 6 buttons here, along with the right shoulder button, one of the shift registers, lithium-ion battery that we have left over from electromagnetic field, a lithium-ion charger, which outputs the same voltage as the battery, other shift register, electrolytic capacitor to smooth the voltage, the client, ESP8266 indicator LEDs, and the left shoulder button. Here's the front of the unit. We have pretty much everything in place on the inside. We're just waiting on the backs. So I have the 2 3D printers in a race right now. The Flash Forge is printing the back using the Protopasta carbon fiber PLA, and the old MakerBot is printing the same thing using regular old black PLA. So we'll see which one comes out the best. They should probably come out at around the same time, and then that's the one we'll attach to finish the controller section. The winner of the print-off was the Flash Forge, which printed a carbon fiber version of the backing piece. Yeah, I haven't cleaned it up completely yet. Yeah, I like the black and silver look, although it's got some overhang issues. I guess I could have reduced that by making the fillet a little less extreme. Also, these holes that the shoulder button rotation pieces go into need to be a little deeper. I mean, the size feels good. It needs to be sanded. Not bad, not bad. Let's check out the PLA one. This is the PLA version. Interesting texture on the inside. I wish it was on purpose. Picked up a lot of hairspray residue on the back. That's not good. But the inside of it is pretty clean. I wonder if I should reduce the fillet on the back. I don't know, it's not super great. Also, the overhangs with these screws, since it prints like this, there's a recess for the screw, but that tends to hang down a little bit. That's not super great. I don't know. You know, the carbon fiber definitely looks better, but I mean, half the problem with this one is just all the residue off the print head. I think I'm gonna go with the carbon fiber version. It needs some cleanup though. It doesn't look as polished, literally, as this other piece does. Okay, well, I'll try cleaning up this carbon fiber one and see if it will look acceptable. We're gonna do a distance test. We have a module hooked up to this laptop, and when the system is receiving zeros and ones, they'll scroll on the screen. All right.
It's changing.
Yeah, can you guys keep an eye on this and let me know if we're still getting changes in the data?
Yeah, sure.
All right, I'm gonna walk away and reconnect this multiple times at multiple distances, and we'll see if it still works. Okay, disconnected, connecting, connected. All right, pushing buttons.
Good to go.
All right, moving away. I'm behind a car, connecting. There.
Yep.
Okay, I'm going further away. Now I'm like in Minnesota now, home of the Vikings. Connected?
Connected, yep.
Woo! Well, I think that's probably farther than we would ever need to go in reality. So I wired up this board first. but I was having trouble with it, so I decided to start over. I think I might have done something wrong, I'm not really sure. So I'm taking it one step at a time, or step by step, your favorite show, which took place in Wisconsin. So this has a server board, the 3.3 volt regulator, the reset button, and some test lines. I have 2 of the output shift registers hooked up to it, so I'm just gonna do a test right now to make sure it works with the Nintendo's power supply. If this gets a signal, the light will blink blue rapidly as data comes in. I'm going to turn on the Nintendo. Looks like the module's working. So I'm going to turn on the transmitter, also known as the controller. Let's see if it'll connect. There it goes. And the blue light is flashing. Cool. So this is working more reliably than the old board was already. Let's do another test. I'm going to have Max press buttons off camera. There we go. Press the left shoulder button. Cool. All right, it's getting a signal. So that's good. So the Nintendo has enough power for this device. What I'm going to do next is hook up the Nintendo shift registers and see if the output shift registers continue to work. Because the Nintendo has input shift registers that have open collector inputs, which means they need pull-ups. And I'm hoping I can use them with the 74HC595 output registers and it'll still work. So the output shift registers will act as the button presses did on the original Nintendo controller. So we're basically emulating a Nintendo controller. So a Super Nintendo controller has 2 shift registers in it. Nintendo controller only has 1. I wired up the first shift register, which will be enough to test the Nintendo functionality. Turn on the screen, turn on the Nintendo, which also turns on the receiver. Castlevania, great. Turning on the transmitter, connected, all right. Hey, we started the game. All right, at least one button works. We don't have any sound hooked up, so I'll have to put in my own. I'll go for the secret. Oh, I missed it. All right, I'm going to continue hooking up the wires for the Super Nintendo. Okay, we're going to test out this controller with the Super Nintendo and one of my favorite Super Nintendo games, Sunset Riders. Yeah, look at that guy's face.
It's weird that his like distant eye is all bug-eyed and sticking out.
Yeah. Well, you know, they didn't have very good doctors back then. He was probably born with a weird condition and they're like, well, whatever, you're just gonna have to deal with it. It's like, he's probably gonna die at age 3 anyway. Whoa! Oh, I almost got shot.
Look out, watch out!
Ah! Yeah, I got a turkey. Just like Castlevania, there's turkeys to eat.
Sure it wasn't like a pheasant? Could have been a pheasant.
That's true. I mean, the graphics aren't
or a
that
goose.
great. Yeah.
It was a goose.
Or a duck.
See, I've gotten unused to the old style video games where you have unlimited ammo.
Yeah.
So I'm used to like, oh no, I have to conserve my bullets. I can't just fire at everything, which is bad because I also have terrible aim. So.
Of course, also in these old games, one hit kills you.
Well, yeah.
Yeah, there is some lag. Maybe we can fix that with the kernel. Whoa, no! I blew myself up!
Wow, there was like guts down in the water.
Yeah.
Uh-oh. Watch out for those radioactive bullets.
Is that like a radioactive car?
Radioactive bullets?
Oh, wait, technically, you know, that's a real thing because they have depleted uranium rounds, you know? Well, I guess it's depleted, not. Oh, I think I'm dead. Well, that worked out pretty well. Now we can play Super Nintendo 5 feet away or 100 feet away. I got this retro controller at the game store. It was like $8. And it has 6 buttons. That way you could play one of the 15 Genesis games that uses the 6-button mode, like Street Fighter Championship Edition and Eternal Champions. Let's see what's inside of this thing. This thing is awfully cheap. I'm assuming it's going to be a glop top ASIC. ASIC is application-specific integrated circuit. So if you see a custom chip inside of something, it's an ASIC. And glop top is when they put the ASIC directly onto the PCB for cheapness, and then they put epoxy over it. Yep. A glop top. But, you know what you could probably do is just cut this down and then stick it on, oh, that's the wrong one. Stick it on the end of the board, see, like that. Not the worst idea. I'll take a photo of this and then hit it with the bandsaw. Okay, here's the cut down Sega Genesis controller. I can hit it with the Dremel and reveal the copper, or whatever they used on this. That should be enough. Now I can tin those parts and give myself connection points. So one question that I would have with this is, you know, what is the state of this little ASIC? Is it going to cause errors with the other functions? Because like the Nintendo controller, that's basically an input. You know, you're always just putting things into it, so it doesn't really matter what's on the line. It's not going to affect anything. But this has like mode switching and a bunch of weird integrated circuits, as I talked about, so I'm not really sure what its effect will be on the other devices. And you know, you might think, oh, you can just, you know, disconnect it, have it off. And that might put it into tri-state, you know, the fact where it wouldn't affect anything, but then again, it might not. So I guess the best thing to do is to hook it up, see if it affects the Nintendo negatively, and then hook it up to a Sega Genesis and see if it works. Why wire up 5 integrated circuits when you can just hack down an existing board? Give me Genesis!
There you go.
All right, now that I have Genesis, I have the Genesis device. All right, let's see if this works. Plug it in, turn on the screen, turn on the Genesis. Okay, the light came on, that's good, I guess. Let's see if we can connect. There we go. Okay, I picked up Eternal Champions. It was only like $1 because it's a 6-button game because it's a fighting game. Come on, fade in already. I don't like it when games are like, ooh, you have to watch this fade in and watch this scroll and all this stuff before you can actually play. All right, this should use all 6 buttons. Let's see. Oh, that's a cheating move. Okay, so yeah, we got the punches here. Looks like we have strong punch, medium punch, light punch. That's good. And the kicks should be on the bottom, just like, almost at Star Trek, just like Street Fighter. All right, this guy's pretty tough for the first opponent. Okay, light kick, medium kick, strong kick. Okay, cool. Of course, the shoulder buttons won't do anything in this game. This game isn't that great. No wonder it only costs $1. I should have picked up Street Fighter, but that would have probably cost like more money. There aren't actually a lot of Genesis games that use the 6-button mode, but I figured if it was going to be a Genesis compatible controller, it might as well have all the options. Oh, I think this stage is like in Vietnam or something because there's like a helicopter in the background and a palm tree. So I guess that's the only place it could be. Hey, I beat him! Sweet! All right, we've tested it with the Nintendo, Super Nintendo, and Sega Genesis. Well, Karen, we did it. We made a wireless video game controller that works with multiple consoles.
I'm playing right now because it reaches the other room.
Yeah, you could do that. So what do you think we should do differently if we ever made another one of these?
Well, one, this port, I occasionally poke it with my finger, so if there's any way to move it more centrally on the back.
Yeah, originally this was going to be a little thicker. That was going to be flush, but then I made it thin to make it easier to print.
Wow.
Because we actually had to print the rear of it a couple times to get it right.
Well, and I like that it's thinner, because
Yeah.
everything smaller is better, right?
Yeah, well, you could actually cut those down. They would probably still make contact. And actually, it's conceivable that the conductivity of your flesh could affect the signaling too.
Oh.
Possibly.
I also think that smoothing out the buttons, or maybe adding some funky foam little pads on them would make it a little more comfortable.
What if we put them with like a tumbler, you know, and not the website, you know, like a rock tumbler?
So I mean, tumblers tend to remove some material along with just smoothing, so they might become deformed. I mean, maybe if before we had put them in, we sanded down the surfaces a little better.
Yeah, instead of not
Maybe.
at all.
Yeah, that.
Well, that's all the time we have for today. Have you ever built a customized retro controller before? What kind of cool things would you like to see us do with old video game systems?
Let us know on the Element 14 community on element14.com/TBHS.
You can also go there to read about other upcoming episodes, builds, and special events. We'll see you next time. Let's play some games. Yeah. We can like play a game over there, and then the screen will be over there. I'm keeping my sloth, baby. Now, woo, we're going to the trailer house. It's not good enough. Hey, maybe I could ask you to give me Genesis off camera, and then you can give me Genesis. Do not take me for a super fan of Cheap Trick. Then it would cut to like Gandalf dancing.
I want you to want me.
Well, it looks like I'm a planet. A little bit on Friday after we left, so we have some progress. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.